For those of you who are paying attention to me, you will notice that I just finished. Anyway, it's a pleasure to be here to talk to you about what the opportunities and challenges of Southeast Asia. Let me, and am I okay? Give subtitles a try, turn on. No, I don't want to turn on that. Okay. All right, great. Anyway, quick reminder of where we're going. This is the global average temperature from 1850 to 2024 or 25, and this is 1.5 degrees where my arrow is now. And so we are passing the original UN goal of 1.5 degrees. But it's worse than that. What many people don't realize is the oceans are actually quite cold. Anyone who's scuba dived know that you go a few meters down, the water begins to get very cold, and you go 100 meters down, it's very, very cold. Average depth of the oceans, 2 or 3 kilometers, 2 degrees above freezing. And so very slow mixing times, and roughly 90% of the additional heat trapped in the earth due to greenhouse gases is actually going to warm up the ocean. And as we warm up the ocean, the surface temperature of the ocean and land, which determines our weather and hence our climate, isn't going to be seen for maybe 50 or 100 years. So that's so what you see now and what you think you're going to see, you have to wait a sufficient amount of time before we actually see what we've done. And I liken it to smoking cigarettes. If you're young and you smoke cigarettes for 20, 30 years, you start to get a series of mutations, and it may not catch up for you until you're 60, 70, or 80, and then you can get heart disease, lung cancer, and other things. Okay, where are we heading? This is the annual emissions that we think we should go down to 2 degrees, for example. By the end of this century, it has to go to 0, 1.5 degrees sooner than that. And so where we are now is on the path somewhere between no climate policies and current policies. And most of the countries, and these are policies that have been declared, let's say, at the Conference of Parties, the COP meetings. And so it looks as though we're heading towards 3 degrees, maybe higher. To get to zero emissions is very, very hard. And the other thing you should be reminded of is that refugees, when you have failed economies or countries that are in strife, war, for example, you create a lot of refugees, and that has transformed politics in the world in the last couple of decades. Now, it's also important to realize that energy, when you're a developing country, is crucial to prosperity. And so this is a graph of electricity consumption of different countries and human development index, which is a measure of prosperity beyond just gross national income per capita, because it also includes life expectancy at birth, the years of schooling. And what you see is that when you're very, very poor, the human development index rises dramatically. But then after a while, by the time you're at the development of a Denmark, a UK, and others, your quality of life does not actually increase that much. It plateaus. And so the question is, how do you get countries in this range over here to be down here? And how do you bring up countries in this range over here to be up here as well? This is particularly germane in Southeast Asia. This is a graph I found today looking at, from the IEA, Southeast Asia Energy Outlook. And this is the growth in Southeast Asia compared to Middle East, Africa, China, Eurasia, Japan. And so a lot of the growth in the coming couple of decades is projected to be in Southeast Asia, a lot of the energy, new energy. Now, this is a problem of how do you make this transition, because getting to zero greenhouse gases is determined by all sectors of the economy, just not, let's say, electricity production or transportation and electric vehicles. And so that means we've got to eliminate greenhouse gas emission from all the things we make in terms of steel, concrete, plastics, chemicals, textiles. And most important, and you've heard a lot about this today in food production is roughly 1/4 of all greenhouse gas emissions, not only in the form of carbon dioxide, but in methane and even harder N2O emissions. I'll talk a little bit about that. So there's good news. The good news is that renewable energy is becoming competitive, not quite, but these are countries in Southeast Asia, I found again from the International Renewable Energy Agency, biomass, geothermal, solar photovoltaic, and wind. And you see that they're getting close to levelized costs where fossil fuel may be, but still not there yet. So that's good news. Alternative clean energy is becoming cheaper. But in fact, we're going to need another industrial revolution because the levelized cost of electricity is not the full story. Once you go to more than 50, 60% of renewable energy, you actually have to include in the cost of renewable energy all the backup systems to keep the lights on and the factories running. And that means enhanced transmission distribution systems, backup generating capacity, energy storage. And so it really has to be, roughly speaking, twice as inexpensive as fossil fuel, because the real cost is all these other things as well. Now, it turns out, because Southeast Asia is part of the Ring of Fire, Indonesia, for example, has tremendous amount of geothermal energy. It has right now 2.4 gigawatts of geothermal with plans to grow to 5 by 2035. But the full potential could be an order of magnitude higher. And so the question is, can geothermal actually be economically competitive with coal? It's not at the moment. It's at least twofold more expensive. But there's some good news. There's a company that was funded by RPE and helped at Stanford called Fervo Energy. And they are actually assembling some of the known technologies in drilling, like horizontal drilling. You can go down, you can go sideways, and you can put that bit within a few meters of where you want it. And so you can actually go into rock formations, you can fracture that rock, and you can put in fluids that help transfer the heat out. And so Fervo Energy is beginning to make inroads in lowering the costs of geothermal. There's a couple hundred megawatt station going in today. And so I urge you people in Southeast Asia to go and talk to this company. This is a technology, it's combining existing technologies in a good way. And the hope is that it will reduce clean energy, especially in Indonesia. Okay. All right. Having said all that, all the good news, we still need, until we get very inexpensive chemical batteries, because if you don't have mountains, you're going to need some form of energy storage. But until we get that, we're going to still need compact turn-on sources of energy. And those choices actually are coal, natural gas with carbon capture and sequestration, or fission with spent fuel disposal. A few comments on nuclear energy, fission energy. If you look at the safety of nuclear energy in terms of deaths per terawatt hour of electricity produced, it's pretty safe. Leading the death rate is brown coal because of all the noxious particulate matter, the SOx and NOx and everything. So here's brown coal, oil, burning wood chips turns out to be about 100 times more dangerous to your health than nuclear. Nuclear is somewhere between wind and solar in terms of safety. People do fall off of wind turbines. There are mining accidents in nuclear. Solar, I guess they fall off of roofs. Okay. But it's 100 times less dangerous than burning wood chips, as Denmark does. So, but people don't realize that about a third of your background radiation is in the food you eat. And so these are naturally radioactive foods. Brazil nuts leads, but bananas, carrots, red meat, even beer and peanut butter has radiation in it. And because of that, a new dose of radiation has been enacted. It's called a BED, a banana equivalent dose. In Asia, it turns out BED could stand for a bok choy equivalent dose. A cup of bok choy is about equal to one banana. Now, but it's in all your food. Now, so the question is this really dangerous? And if you ask the FDA, the NIH, and they will say, no, it's not dangerous. You're better off eating your greens and spinach and other things than not. Because the amount of radiation, background radiation, can vary by fivefold. But there's no, in terms of where you live, because you can live in radioactive rock regions, or and how many bananas you eat, or spinach. But there's no correlation between background radiation and incidence of cancer over factors of 5. Okay, so that's one thing. Now another thing, and there'll be another session tomorrow. There'll be a discussion on this about whether we can actually see nuclear energy come back. I don't really know. But a lot of the hyperscalers, these are Amazon, Meta, Google, and Microsoft, are beginning to look at nuclear energy as a way of powering their very large servers. And these are two examples of nuclear reactors, new technology in nuclear reactors. This one has already been approved. This one is yet to be approved. And so this is an issue that could be very good. If you make thousands of these, that means you can actually get on a learning curve and then begin to ship them around the world. It's inherently much easier to design these smaller reactors so that the chance of a meltdown is far, far less. And that would be very important for many, many areas around the world. You do not want a contamination event. So, but we don't know whether you can build these small nuclear reactors on time. But I wanted to mention one thing in particular, and that's spent fuel disposal. If you're in a country now and have nuclear power, you're obligated to try to put your spent fuel, reactor fuel, somewhere in your country. That, for example, would be impossible in a place like Singapore. And so I think one has to realize that there are other countries which have lots of land and not a threat to proliferation. I think, Indonesia can be one of them. You've got a lot of islands. Also, Australia, Canada. I used to think Russia, but I guess that's off the table now. But these other countries could get hundreds of millions, maybe billions of dollars a year to be a repository for the spent fuel. And so we need to revisit this so that you can break it and put the spent fuel where it could have at least the least expensive, but also best for this international development of potential nuclear fuel. Okay, so agricultural revolution. We're going to need a fourth agricultural revolution. What was the third agricultural revolution? Well, it was the ability to make nitrogen-based fertilizers artificially, the so-called Haber-Bosch process. And it was also the crossbreeding of crops, begun with Norman Borlaug. Haber and Bosch got 2 Nobel Prizes, Norman Borlaug another Nobel Prize for their contributions to this agricultural revolution. It's pretty impressive. In 1961, there were 3 billion people in the world. And by 1921, there are 7.9, now there's over 8 billion people in the world. The amount of land put under agricultural cereal production did not change. Okay? But the productivity went up threefold. This is a very, very big deal, but there are unintended consequences. Unintended consequence number one is the idea that you have very efficient industrialized agriculture means that you can produce food around the world, but if you're in a local area where you have a drought, a crop failure, a flood, 1 year, 2 years maximum, the local farmers are wiped out. And so what do you do in order to sustain the ability to keep local agriculture going is a very, very big deal. And this is kind of a list of what you can do in terms of protecting against crop failures, climate and biological risks, protection against price collapses. If there's an abundance of food and the price collapses, you can't sell your food at any profit. And finally, there's social protection and resilience building. So I think what happened in the American experience during the Depression is that we had food prices completely collapse, and the government stepped in and said, we'll guarantee a floor in the prices. And we'll do that. And so you need something like that in developing countries in order to preserve the farmers and the local production of food. That's incredibly important. And so this is one of the, there's good things about trade and macroeconomy and all this other stuff, but there are some bad things about it because it can affect people locally. Let me talk about agriculture in terms of greenhouse gases. It turns out that if you put fertilizer in fields, and we're going to be using increasing fertilizer as the population grows, the fertilizer that's not absorbed by the plant, it gets turned into N2O by microbes in the soil. That N2O is a very bad greenhouse gas. It's about 300 times worse than carbon dioxide, and it lasts 100 years. And the question is, can you get rid of N2O but you can't get rid of fertilizer? And so it may be that the solution may end up in a new area called synthetic biology. This is where you can take a microbe and you can alter its genomic structure. And this is a proof of principle effort has been done already in the Bay Area, where microbes have been altered so that they can enter into symbiotic relationships with plants, let's say corn. And so the corn, these microbes are near the boundary of the roots and the soil, and the plant says, feed me, and the microbes feed. And in this experiment it's actually had field testing for now a half dozen years, it's eliminated about half the fertilizer needed for corn. That's the good news. The bad news is it only is half the fertilizer, and soils in different places have different microbiota genomes, and it took too long to develop. I was in the board of directors of this company that worked with Pivot Bio, and it took 8 years, and the company went bankrupt. So what I think is going to have to happen, and what I'm working in my own lab, is to be able to introduce not one gene, one promoter at a time, but maybe a dozen, so that the speed of testing and optimizing these microbes can increase combinatorially. And so this is the big hang-up in terms of synthetic biology. And because you can type out the DNA just on a typewriter, so if you can get it into microbes, it would be a very big deal. Okay, so let's go back to CO2. We're likely going to go over 550 parts per million. As I told you, there's other sources. And we're emitting over 40 gigatons of CO2, but if you include all the other greenhouse gases, maybe over 50 gigatons of carbon dioxide equivalent. That's a lot of carbon dioxide and other greenhouse gases. And you think because of agriculture and other hard to abate areas, you would need at least 10 billion tons of direct air capture and another 10 billion tons of point source capture in the world until we can get rid of some of the things like agriculture. So that's the problem. And as I want to emphasize, the worst effects of climate change will occur in future centuries. But the good news is, unlike cancer mutations, if you get rid of the carbon dioxide, and the earth will cool down, and most of the damage will be done not in this century, but in future centuries. And so we believe that the earth can heal itself. But you've got to do this. You've got 100 years, maybe a little more, but you've got to do this. Where are we now in carbon capture? Well, not in a good spot. This is a project I funded when I was Secretary of Energy. It costs $1 billion. It takes an acre of land to capture 1/4 of the carbon dioxide emissions from a pretty large coal plant. That's 1 million tons a year. And you're not going to be doing this over gigaton scale or tens of gigaton scale because it's just simply too expensive. And the reason is capturing CO2 and anything that forms a covalent bond is fundamentally a bad idea. Because once you form that covalent bond, if you want to release it to sequester it, for example, by pumping it underground in geological formations, you've got to pay that price. If you turn it into something else and don't release it, that's fine. So let me tell you of one possibility, and that is it won the Musk's Carbon X Prize for carbon removal, $50 million. And what it does is it takes basalt rock. This is volcanic rock that you have in abundance in Indonesia and other places. You grind it into a fine powder. You sprinkle it on agricultural fields. When you sprinkle on agricultural fields, this basalt rock turns silicates into carbonates. The carbonates are a dissolved form of carbon dioxide, which naturally leaches out of the soil, and it eventually goes into groundwater and finally drains into the ocean. So this is a potential, and once it goes in the ocean, it's really long-term storage. In a field test for this MATI carbon capture, they also showed that in fields in the Corn Belt in Illinois, that the productivity of the crops increased by 12%. Estimates are over the map, but perhaps 80 to 220 tons of capture per year. And so I'm raising this because part of the money, a lot of the money has to come from developed countries. So to transfer to developing countries, as was said several times in this meeting, but some of it can come, and we're really talking about billions potentially, can come from a carbon trading market. This reforestation or things that can sequester carbon dioxide, such as this. There are other possible methods of capturing carbon dioxide. One is that it's known that if you have a body of water, a hunk of water, Olympic-sized swimming pools full of water that have high pH of 11 or 12, you can put a lot of carbon into that water. And if you shift the pH from 11 or 12 to 6, the solubility of carbon dioxide actually changes dramatically by 4.5 orders of magnitude. And so that has gathered a lot of attention. Can you shift the pH in a clever way? And we stumbled on possibly a clever way that could reduce the cost of air capture by an order of magnitude of what is being done today. We don't really know until we try it and scale it up. But if you can get air capture at $60 a ton, it could be deployed. Above $100 a ton, I don't think any kind of carbon capture will be deployed. So that's a possibility. Now, let me do the final topic. It's really impossible to talk about any path to sustainable future without talking about population growth. It's the 80-ton gorilla in the room. This is the population history from 1 million years ago to now. And in the last billion, it didn't take 13 years as projected by this science article. It took only 11 years. And so the question is how much is this going to continue? And if it does continue, and if these people go to a world of rising prosperity as they want to, as is their right, what will happen to the earth? And so it turns out that virtually to increase economic prosperity, and virtually all countries is based on having more younger workers support a smaller aging population. It's like more new investors to support older aging investors. That's known as a Ponzi scheme. So you don't even have to be profitable as long as you continue to get more new investors. So the issue, though, is that when people across all cultures, all societies, they are choosing to have fewer or no children. And so rather than offering tax incentives to make more babies, we should figure out really what to do. In the long arc of history, think about the transition we made from farming to once it's mechanized farming, you don't need that many farmers. And those displaced workers went into cities and went into manufacturing jobs. They made cars and washing machines and other things. And so the question is now, when you're making cars and washing machines and other things, if you don't automate, you're going to be left behind. And so those jobs will slowly begin to disappear. And so the question is, what do you do about this? And I think the answer is, and we have to start thinking about this transition. It's not going to take a decade, it'll take longer, but how do you actually get robots to begin to take over all the dirty, dangerous, and disgusting jobs that we now have that are minimum wage? And so this is what we need. We also need a new measure, different measure of wealth. And the current measure is the gross domestic product. And so what do we really care about when we're a developed country? We want to be able to know that our families and our neighborhoods, our kids are safe. We can send them down the block and they can play in a schoolyard without being mugged or robbed or sold drugs. We want to be healthy and vital and we want to be connected in our old age. So I want to nearly end this with a quote from Robert Kennedy Sr., not Jr. And he said the following: the gross national product does not allow for the health of our children, the quality of their education, or the joy of their play. It does not include the beauty of our poetry or the strength of our marriages, the intelligence of our public debate, or the integrity of our public officials. It measures neither our wit nor our courage, neither our wisdom nor our learning, neither our compassion nor our devotion to our country. It measures everything, in short, except that which makes life worthwhile. How fall from the tree? Someone can fall, I don't know. But anyway, I want to summarize, where are we going? And what's our current path? If you look at the history of the United States, we went from wood to coal, and then from coal to petroleum and natural gas. And here you see a trickle of nuclear, hydro, and other renewables. And so you look at this and you're encouraged. You say, wow, that's pretty good. 60 years, maybe, to do this? No, it's actually worse than that. If you look at what the world is doing, every time you find a new energy source, it just adds to it. Okay. And coal will be around until we find something cheaper than coal, and it will be used. And so with that, I'm going to, I hope this works. I'm going to show you a little clip from the movie Titanic. So here goes. If you can lower the lights, please. Someone lower the lights. Down, 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 down. Okay, good. Okay, anyway, you know what happens. The bottom line is it takes 3/4 of a century to turn the ship. Not even 60 years. And that doesn't mean we should not do a hard right rudder now. We should. But bear in mind, it's a long, hard journey, but something we've got to do. Thank you.